Okay, go ahead now.
Yeah. So it's my pleasure to welcome Professor Seshimohan Srivastava to this colloquium talk at Ashoka University. He is a very well-known and distinguished specialist in logic and descriptive set theory. He has retired from Indian Statistical Institute and he is currently an NBHM visiting fellow at Institute for Cultivation of Science in Kolkata. And Professor Srivastava is also very well-known expositor. He has written several books, both at undergraduate and graduate level, and some of them have really become standard reference in this field. So, without much ado, over to Seshman.
Thank you. So, thanks a lot. And hello, Maya.
Hi, SMS. Happy birthday.
Happy birthday. Thank you. Thank you. Where are you? Are you in US?
No, I'm in my room at home.
Ah, beautiful picture.
Yes, I'm just pretending to be in San Francisco.
Did you see, ma'am?
I can see the top of her head. Hello, madam.
Hello.
Oh my nice to see you.
Okay. So there is one correction I want to make in biography that was written. It is said, it's given the impression that my book, forthcoming book in set theory, is accepted by American American Mathematical Society. That is, if TXX remembers Vikas, then answer is yes and no. So answer is yes, because the referee reports and editors' reports were positive, but it was subject to very serious revisions. So I have revised and I have sent. And at the moment, latest report to me is that it is they are doing market survey. How good is the market of set theory? And that is where it stands. So very strictly speaking, it is not right to say that it is going to be published by AMS. But I may have said, because I'm an optimist, I always hope for the best. So I may have said that, oh, it is going to be published. But subject to this, it is this. So that correction I make. And I also thank Ashoka University to invite me for this talk. I'm particularly happy because so many of my friends and Maya remembers my sign off in my story and forge. They are present here from ISI. And lot of students and such. And so that's it. So, and another thing that I want to tell is that it is really a storytelling, but it's a very interesting storytelling that how suddenly set theory was discovered, because given the era, having such a subject, how did it come? It was not at all there. And so there must have been a good reason for it. Incidentally, I have written an article on it in Resonance some time ago. How did Cantor discover set theory and topology? So this is a part of it. And it will come in my forthcoming book, An Invitation to Set Theory. So now I am sharing the screen. Okay, so it is really the story of the birth. So one thing if somebody is expecting to learn set theory, again, answer is yes and no, because I will not. I will tell how Cantor came down to developing set theory. So naturally, some concepts will come, which was in the beginning, and that got started. And those concepts are the central concepts of set theory, namely ordinal numbers and cardinal numbers. And so that is the most central concept in set theory. And the technique of extending induction beyond natural numbers. So let us go. So this is the story I am going to say. I have already told. And so, well, this was the importance. I really feel that it had a profound impact. And now somehow when one thinks that, you know, how earlier people used to talk of mathematics, convey mathematics. Because for us, that is the set theory is the most convenient language. And again, I tell you that it is a very elementary talk. And if one does not know the story, then it is okay. Otherwise, the talk will be very elementary. So I am going back to mid-19th century or even earlier, that what was the scenario of mathematics like then? And then in that scenario, how did he think of set theory? How did he come to discover set theory? Makes is a good question, and that's what. So let us begin. That it's not that set theory is needed to do great mathematics. Even before set theory came, there were a lot of contributions, very great discoveries. The big names: Brahmagupta, Euler, Galois, Gauss, and so on. So we know that a whole lot of mathematics was developed by that time. And so the scenario was that then mathematics used to be, so to speak, concrete, with mathematicians working on, let me go up a bit. No, this is not the right thing to do.
You can view full screen if you want. Then it will come as a presentation.
How does one do?
I think
Control L.
Control F or L.
L.
There you go. Now it's full screen, yes.
Yes. Okay. So now what I'm saying is that at that time, mathematics used to be, you know, so to speak, concrete. I mean, what is concrete? We understand. And people were working with such fundamental concepts like numbers, polynomials, curves, surfaces, and so on, and used to handle them and prove great theorems, but without being So at that time, they were not very much bothered about definitions or systematically developed theories, starting with axioms. The only example that I know of is the development of Euclidean geometry, as we traditionally know it from our school training, by Euclid. Otherwise, you know, things were in that sense not very formally, used to be developed formally. People had a concept of what are numbers, what are real numbers, complex numbers, curves, so on and so forth. Yeah, I mean, even surprisingly, the notion of functions and such were not very precisely defined. And intuition and technical power of those mathematicians played a very significant role in the development. So far as I know, even the sum of infinite series, or it's kind of limit kind of concept. So in limiting case, what would be the values of certain variables or sequences? That was understood intuitively. Now, one example that one can one knows, even it's very well known, is that Galois headed straight to show unsolvability of problems of degree 5 using radicals, almost from, just handling polynomials, nothing more. Even though, that occurred in the era of modern algebra, and I hope Amatta is not listening. And okay, and these Galois groups playing a very vital role. Even now, if you suddenly enter a room, G sub L, this, that, G is standing for Galois in all advanced, fancy mathematics, where are even done there. So you can see that, without being formal, he proved such a thing, which is still, having its impact and helping in development of mathematics. So in this scenario, it is so this is what I was saying, that how did Cantor discover set theory becomes a very good question, because things were quite different looking, quite different, approach was very different. And then how did this sudden abstract, very general things came up? And we all agree that no great discovery is made without it becoming necessary. So as it said, what is it, the statement? Necessity is the mother of all discovery.
Mother of invention.
Mother of invention. Okay. So what made it necessary? For there must be something that made that compelled or Cantor had no option but to develop. So let me just tell you a few words on Cantor. He was a very hard-headed mathematician, and I consider him even now a mathematician, completely like any of us, because he only approached the problems, very concrete problems, and his thesis was in number theory under Kume, and so this already I have done that. What compelled him to develop such a very general and abstract theory, which is called set theory now, at that time. And we know the impact of this in mathematics. There were several discussions with the paradoxes coming and such, which forced, which even created doubts in the mind of many mathematicians, whether mathematics rests on solid logical foundation or not. So it led to that. And this is what I am saying, that now even the language of mathematics is very, very much influenced by set theory, and even way of doing mathematics is very much influenced. It's almost kind of set theoretic way of thinking. So after his thesis work and such, spending some time here there, finally he joined in a university at Halle University in Germany. And Heine, same Heine as Heine-Borel theorem fame. So Heine was a faculty there. So we came in contact with Heine. And Heine gave him a problem, the following problem from the Fourier series. Okay. And in my opinion, Rajendra is here, still I am saying that Fourier series or the work of Fourier is the single most important result to develop modern knowledge. But lot of great people started. I mean, he was not very precise in what he was saying. And in order to make it precise, to understand what Fourier is doing, the whole lot of, I mean, so to speak, it started analysis. And this is my personal opinion. If somebody disagree with me and says that no, there were other factors, calculus and such. But I would say that, you know, to make things precise, this one was the single, this was the most important work done by things. So anyway, there was a question which was open, that can a function f have more than one representation by a trigonometric series? Okay, and I will make it precise in a moment. So this is what I mean, that consider this trigonometric series. This was not the language. It was like half a0 plus, you know, a0 sine cos x plus b0, a1 plus cos x plus b, whatever. But forget about this. Let us come to somewhat modern language. So look at this trigonometric series, okay, formally. So students should not mind what does this x twiddle mean. Like they think of polynomials, power series, just think of this, where CNs are, where the CNs are complex numbers or whatever. So you think of this as a formal trigonometric series. And now this is what I meant by representation, that point-wise, suppose this series converges to 0. Okay, does it follow that all CNs are 0? In other words, if in limiting value the series becomes identically equal to 0, only if and only if each Cn is 0. And so that explains, can a function f have more than one representation by a trigonometric series? So this question was not resolved that time, and people were worrying about it and giving special cases under very restrictive conditions. People were proving this. Not that nothing was known. No special cases were not proved. That is not true. But in general, in its generality, it was not known. And as I understand, and by reading some of the literature, that all these people put their mind to this, and still the problem was. So, as you can guess now, in order to solve this, and slowly he got into set theory. So let us proceed. So Cantor answered this question in the affirmative, that yes, if you look at point-wise convergence, then a function cannot have more than one. I mean, they may not have a full trigonometric series expansion. That is not guaranteed, but it cannot have more than one trigonometric series. That means two sequences, different sequences, where the corresponding series converges to same point for each x. He answered that, and analyzing this and that, slowly, he got into set theory. So I'm going to prove this result, because it is while Cantor started analyzing his proof and generalizing his result, slowly he had to get into set theory. And to understand that, it is necessary for me to tell you the proof of this, modulo some assumptions, some theorem. Okay, so one of the theorem that Cantor used, and which will be used in the proof, is all the students are familiar with this, who do differentiation, that take any function f on an interval and consider this fx plus h plus fx minus h minus 2f. Okay, divide that by h square. Okay, and so at the moment I have not assumed, I have only assumed in this theorem, in this Convergence theorem, that f is continuous. And the result was needed for that. For was to be applied, the proof was to, this proof was to be applied on certain function which is continuous only, you don't know more. And this is what we define d square fx. Even, I mean, because this can be defined, this may exist, may not exist. I'm not saying that, but define d square fx like this. So assume that for all x in an open interval a, b, this exists. Now, if dx square f is greater than equal to 0 on AB, then f is convex. And let me open the next line, then I will again go back. That suppose your f is twice continuously differentiable. Okay? So, in that case, using mean value theorem twice and continuity of the second order derivative, you will see that dx square f, this term is nothing but the second order derivative. Okay? In case f is C2 function, what is called C2 function, twice continuously differentiable. And at least in analysis, it is certainly taught that if second order derivative is greater than equal to 0, then the function f is convex. But this is true even without this assumption. Okay, so that is Convergence theorem. But if dx square f is greater than equal to 0 on AB, then f is convex. Now suppose dx square f equal to 0, then also f is convex, and dx square minus f will also be 0, because if you replace f by minus f, you get the minus. So if dx square f becomes equal to 0, then f is both convex and concave, and therefore linear. Okay, and this is the part that we are going to use. So this theorem, if you fall back, if you assume f is twice continuously differentiable, then this portion is, this result is done in BSc analysis classes. But the result is true for continuous function also, and may not be very hard. But in any case, now there is one more result which I need. So already this limit has been talked of. So if this limit exists, we say that this series or this series of trigonometric function is convergent. Now consider the following function. Okay. Now look at it. How do I get this function? What is the relationship with this function and that function? You integrate this term twice. Okay, term-wise. I mean, integrate this term-wise twice. You get precisely this. Okay, so C0, integrate it twice, you will get one C0x, then another time integration C0x. Similarly here you can see. Okay, and minus comes because I square is minus. Okay, so this is a series. This is a thing that we obtain by term-wise differentiating. And now notice here that 1 by n square occurs here, n square. And we all know that series 1 by nx square, summation 1 by nx square is finite. Okay? So, if these CNs, this is anyway continuous, don't worry about it. If these CNs are bounded, then by Weierstrass M test, you will see that this series is uniformly convergent. And that is what will make this function continuous. Okay? So, and on this, I am going to play the game on this function. So, if you integrate term-wise twice and use Weierstrass M test, get uniform continuity. If assuming Cn is bounded, then this becomes a continuous. And then there is a lemma by Riemann that if this is bounded and original series converges to X, you see I got F by integrating term-wise the series. And I am doing the reverse operation as if I am taking the second derivative. Okay? So this dx square, you can think of reverse of integrating twice. So if Cn is bounded and if this is converges to S, then this guy exists and equals to the same. Okay? So this is a result due to Riemann, which was known. Now, Cantor made the following observation. This was his first observation while attacking the problem, that if X converges to 0, that is our assumption. If that series converges to 0, then whether all coefficients are 0 or not. So this is the assumption given to Cantor. So if X converges to 0 for all X in a non-empty open interval, then the coefficients will go to 0. Okay? Not a very hard proof, but Cantor observed. As mod n goes to infinity. Okay? So both ways it goes to 0. Towards plus infinity and minus infinity, both ways it goes to 0. He made this observation. And therefore, CNs are bounded. Okay? Any sequence that is convergent is bounded. Okay. Now here comes the main idea. That suppose let Cn be bounded, then you have this function. And once it is bounded, I have already told you that it is a continuous function going to be used. Suppose somehow I can show that this fellow is linear. Okay? Suppose I can show that in the beginning it was just for all real number R, this goes to 0. So suppose for all real number R, this is equal to, this is linear. Then all Cn will be 0. Okay? So he started this, reduce the problem to show that Cn is 0. All that he has to do is that he has to show that this series, this function is linear. So how does it prove it? So we are assuming that this is linear. Now in this, if you put x equal to pi and x equal to minus pi, then this left-hand side becomes 0. Okay? Because it is, each term has same value that pi and minus pi. Okay? And and if you subtract, then what happens is that if you subtract, then this side you get 0, and L minus L becomes 0. So what you get is that m times 2 pi is 0. But that will force m to be 0. Okay, that is what is hidden there. So once you have proved m to be 0, this function reduces to be constant. Okay. Now, if you put x equal to 0 and x equal to 2 pi, okay, and subtract, then you will see that, again, because of periodicity, you will see that this is vanishing. No. By substituting x equal to 2 pi, 0 and 2 pi, what happens? This becomes minus L. Just a second, am I right or not? I could be right. Oh, because this goes away. This goes away, and this gives you C0 2 pi x square, okay, and equal to 0, okay? And therefore C0 also becomes 0. Oh, sorry, conclusion is here. So that forces C0 to be 0, okay? So actually this equation reduces to this, okay? This minus has been brought here, this side, that this becomes 0. Now this is uniformly convergent. So you can interchange order of integration and summation. And that's what you do. Take any k not equal to 0. Okay. I'm going to show ck is 0. C0 is 0 is already proved. C0 is 0 is already proved. So you have to show ck is not equal to 0 or k not equal to 0. Okay. And then it is very easy. This is uniformly convergent. So you multiply both sides of this equation by e to the power minus ikx, you know. And yeah, so you do that, and what you are getting is 2 pi into ck by kx square. All other terms, the integral is 0. There's some typo here, but if you see things clearly, you see things write down carefully, then you will see that this becomes this. Okay, but this integral is 0. So you find that this term is 0, and therefore ck is 0. Okay. Now still, this is completely analysis. No set theory, nothing inside. Okay. So now, having shown this, dx square fx equal to 0. So what is this? If x converges to 0 for every real number x, then by Cantor's theorem, Cn goes to 0. And therefore, Cn goes to 0 as mod n goes to infinity. And in particular, Cn is bounded. And therefore, now you come back to this series. Then by Riemann's first lemma, dx square fx equal to 0. And Schwarz tells you that fx is linear. Okay? So this one was under the assumption that if you can prove fx to be this, you will show each Cn is 0. So all that left is to show that this is linear, and that is where you apply Schwarz's lemma. Okay? That is where you apply Schwarz's lemma. And that problem, surprise, I still feel very surprised that why it was open with such big stalwarts in the game. But nonetheless, it is a fact. Okay? Now, Cantor still started thinking. Okay, that here assumption is that for all real x, that series converges to 0. Huh? And he said that no, I can make this theorem better. And he was aware of, again, yet another result of Riemann. Okay? And only difference between this expression and dx square fx is that here is h, not hx square. Okay? And Riemann had shown that if Cn converges to 0 as mod n goes to infinity, so now earlier Riemann's first lemma was under the assumption that Cn is bounded. Now here it is Cn goes to 0. So if Cn goes to 0, then this guy goes to 0. This limit is 0. Okay? So Cantor was aware of this. So you see all the machinery were available to Cantor. Now, Cantor then could see that using Riemann's second lemma, his result can be generalized quite a bit. And that is where slowly set theory comes. So to state the thing, let us call a set D of real numbers a set of uniqueness if whenever this goes to 0 outside D, you don't demand for all x in R, but except for points in D, then each Cn is 0. So this is a definition I am giving, a set of uniqueness. A set D of real numbers is a set of uniqueness if this series converges to 0 outside the set D, then that forces Cn to be 0 for all n. Okay? And if you take D to be empty, that was precisely the problem which was open. Okay? So according to this definition, Cantor had shown, I mean, just now I gave you the proof even, that the empty set is a set of uniqueness. Next, he proved that take a finite set of real numbers. Okay, I have just arranged it because I will use this arrangement. Take a finite set of real numbers. So think of that as D. So if this series converges to 0 at all real numbers except for finitely many points, then also each Cn will be forced to become 0. And let us see how he uses second lemma cleverly. Now, so I had arranged them in increasing sequence. So I have these open intervals. Okay? And by what we did earlier, this f becomes linear on each of these. Okay? This was the earlier argument included in the earlier. Okay? So now we have these f to be linear on each part. But it may be different linear thing, slopes may not be same, but f is continuous. That is also we know. Now he uses Riemann's second lemma. Okay? By Riemann's second lemma, I have written that term rearranged. You mind it is 2fx. So fx plus h minus fx by h minus fx minus h minus fx by h. So you look at this. Okay? Then this is precisely the limit there. And by Riemann's second lemma, it is 0. What it is saying, that the linear function to the left of AI and to the right of AI have the same slope. Okay? Together with the fact that f is continuous. Therefore, that line becomes the thing. The whole thing becomes linear. And then the result follows. Okay? Well, probably ordinary fellow will stop here. But no. Now so from books that I have studied, I mean, somewhat historically describing the development, Weierstrass is the first to define the notion of accumulation. He called them point of condensation. So for the sake of my job here is to say how the set theory was born. I will be only considering closed and bounded set of real numbers. Okay? And since there may be first year undergraduate students, I am not saying that I am only considering compact. Then he defined the notion of derived set, which is the set of all accumulation. See, mind it, he's doing a lot of general topology, and I do give a lot of credit to Tenper for discovering set, topology also. By topology, I mean point set topology. And if something is not an accumulation point, some point of A, then we call it an isolated. Now, if A is a finite set, then obviously there is no accumulation. So the derivative is G. Now, just think of it as follows. That I have an example of a non-empty set whose first derivative is G. Okay, non-empty, closed and bounded is kind of a standing essence, whose derivative is G. So what Cantor does is that take an increasing sequence. This 0 less than A1 is delivered by me. Take an increasing sequence converging to 1. Okay? And this is my A1. That means all these points A1, A2, A3 together with 1. Then 1 is the set of accumulation. But the second derivative is G. Okay? And Cantor shows that such sets, I have written for this particular kind of set, but any set whose second order derivative becomes 0, any closed and bounded set, whose second order derivative becomes 0, is also a set of uniqueness. But nonetheless, to focus the idea of discovering set theory, let us fix such sets. And how do you prove it? Cantor said, oh, I can just prove it in the same way. So, first of all, you take a closed and bounded interval not containing 1. Okay? Then, how many of these points will be there? A1, A2, A3, this. These are isolated points. Okay? So, any of these which is contained in a closed and bounded set, and it has to be a finite set. Okay? So, such a thing which does not contain n, 1 contains ai only for finitely many i's. Okay? So, on each such set, from the argument that we have done, fx is linear. So, for each closed and bounded interval on which does not contain n, 1, this is linear. F is linear. And again apply, so it follows that fx is linear on, it is hidden somewhere, minus infinity to 1 open, and 1 to infinity open. Okay? But the slope may be different. F is continuous. Slope may be different. Now apply Riemann's second lemma. Then you see that the slopes, left-hand slope and right-hand slope are equal. And therefore, fx is linear everywhere. And once fx becomes linear everywhere, we have shown already that all coefficients are 0. But he was a very jiddi admi, Cantor. He will not give up so easily. Now, let me go back to a thing. He said that for any closed set A, and I'm deliberately, so this closed in real numbers, which is closed in R, you go on taking derivative. So you start with A, call it A0, then A1 is the derivative of A0, then A2 is the derivative of A1, and so on. Inductively you are defining. Okay? And he shows that that suppose there is a closed set such that at the n-1th derivative is 1 and nth derivative is empty, then also the set will be a set of uniqueness. And how does he do it? He proves the existence of such sets by induction. So take an increasing sequence, A1, A2, An to 1. Now, between A1 and A2, you can put a replica of a set whose n-1th derivative becomes 0 for the first time. So what I do is that between Ai and Ai plus 1, I get a replica of An, okay, such that n-1th derivative is singleton Ai plus 1. Okay. So whatever set I was building, it was not necessary that it is going to 1. Whichever sequence is converging to increasing to a point, there that kind of argument you continue. So this is singleton 1. And now you take all these sets and then add 1 to it. So when you take n-1th derivative, you get precisely this, singleton 1. You get singleton 1. You get this set, that only the limit points will be left. Okay? Then you take the nth derivative, you get 1. And n plus 1th derivative 0. So such sets for each n exist. And then it was very easy for him to see that all such sets, okay, so again, he didn't know what to call these sets. So he named these sets of first species, sets satisfying this purpose. Okay, I'm only restricting to closed and bounded sets, compact sets. Okay. And he could easily see that, again, the same kind of argument. You know, you take, you prove inductively that f to be linear on each of these intervals, and then apply. So if you take any, closed and bounded interval not containing 1, it will contain only finitely many of these. And then you look at the corresponding portions and do the argument exactly the same way. Then you will find that on each of the closed and bounded intervals not containing 1, this is becoming linear. Okay, and then apply Riemann's first lemma and show that the slopes at each of these points are same, and then by continuity it is linear. So he could see that immediately But this guy was a very obstinate guy. Now, one problem that he faced, that okay, he has to describe this result. But we are at a stage where we have just defined accumulation point. We were at a stage where real number system was not defined. If you, those BSc students, even this is given usually Dedekind cut construction, real number system. Dedekind was around sophisticated one will see that completion of rational numbers is also constructs real numbers. Okay? But these things were not known there. These were not formalized. So in order to put all these, and now we are thinking of already general sets of reals. Okay? Which itself was slightly new at that time, that not a specific set, but a general set of reals. And there is obviously some kind of topology, accumulation points going on, so on, so forth. So these things were not properly discovered. So Cantor at that time gave construction of real numbers as equivalence of equivalence class of Cauchy sequences. So either this is BSc students may not have been taught it this way. They may have been taught as Dedekind cut. But as soon as you start metric spaces, then the completion of metric space is what is needed, involved. And so that is due to Cantor. Okay? And he defined the real numbers system to be the completion of rational numbers. Okay? And I have also, I'm not a natural historian, as my friend Amartya Dattai. Those days, Cauchy sequence actually was defined by Cauchy, but he called them fundamental sequence. So he defined real number systems as completion of rational numbers and proved everything, that it is a field, it is an ordered field, there is an ordering. All these constructions you people know. And then open intervals, and once you know open intervals, then you know the accumulation points and so on. He could define and put his result precisely. Okay, so not only you can see the power of Cantor here, that he is using a lot of analysis. He is using topology. So I do consider him one of the, sort of significant analysts and topologists of that time. Okay. Now, Cantor started thinking, okay, so I have given a lot of examples of sets of uniqueness. But he started thinking of these sets. And one of the things that he noticed is that this taking the successive derivatives, you need not stop at a countable. Okay. And let me show you. So what he meant is that take a sequence converging to increasing to 1. Then here you put a replica of an. That means nth derivative vanishes for the first time. Okay, just what example I have given that. Okay, and finally you take all these sets and take 1. Then if you go on taking derivative, you will lose, you will keep on losing C1, C2, C3, but you will not stop. All the inner derivatives are non-zero. And once you intersect them, you get singleton 1. Okay? Take, points which are common to all these. See, slowly now, various set theoretic concepts are coming. And still set theory was not developed. So instead of using this notation, he used this notation, C infinity, like he was doing, first derivative, second derivative, third derivative, and so on. This is the infinite derivative. Okay, this intersection. Set theory was not yet developed. So this concept was not still there. And he called so once this is a closed and bounded set, we can still talk of its derivative. Okay? And call the derivative of this, he has to use some notation. He called it this, C infinity plus 1. Then he says that, oh, I can get a closed and bounded set such that C infinity is not equal to 0 and infinity plus 1th derivative is 0. But he can proceed, because once you have a set like this, again you take increasing sequence, and between any an and an plus 1, you put a replica of C infinity, okay, such that, when you look at infinity of C infinity, you get singleton an plus 1. So when you take all these things in common, you get this, and then you get C infinity plus 2 to be non-empty, C infinity plus 1 to be non-empty, and C infinity plus 2 to be empty. And you can continue this process. Okay? And it is not very clear, though it is very obvious from the proof in the finite case, that all these are sets of unique. But what was more interesting is that how does he formalize these notions, these kind of sets? Clearly, there is some kind of induction going on. Induction beyond natural numbers. You are not only thinking of A0, A1, A2, A3, AN, and so on. You are also now thinking of A infinity, then A infinity plus 1, then A infinity plus 2, then A infinity plus 3, and so on and so forth. So there is some kind of induction is going on beyond natural numbers. So how does he put it? And this is the first serious set theoretic thing came to thing. I mean, this led to the first serious and probably still very serious concept in set theory, namely extending extension, induction beyond natural. Okay. So, but to describe all these, what are the 0, 1, 2, 3, dot, 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 infinity, infinity plus 1, and this? As if they are stages of construction of set. Okay? But these are completely abstract things in the mind. So the only way he can describe the set of stages is to think in completely general terms. So he asked that on what sets this method of induction can be generalized. Okay? It's not that arbitrarily you can do it. There is a stage-wise construction, what we call inductive. But General mathematicians or mathematicians till that time stopped at induction on natural numbers, but now he is going beyond. So he wants to describe what properties the set of stages should have. Okay, such that on that kind of set, he will extend the method of induction. So it is very clear that given two states, you know which stage comes first and which stage comes later, which just amounts to saying that your set of stages should be linearly ordered set. Second thing is that suppose your construction is not yet complete. Suppose you want to come up to C infinity plus 10, but you have only built C infinity. Still lot of stages are left. Then if you have done come up to certain stage and your set of stages are not exhausted, then there should be the next stage to this. Okay? Which looks like that if you take the tail, because it is linearly ordered, if you take the tail of this set of stages, if it is non-empty, then it has a first element. Okay? Which becomes equivalent to saying that every non-empty set has a first element. Because if you take a non-empty set and look at set of all points which is greater than equal to non-empty subset of real numbers, and if you take set of all points which is bigger than some real number, then you get a tail set in the linearly ordered set. And the first element of both the sets will be the same if they exist. Okay? And that is what I have told you led to the notion of well-orders. Okay? So it is a linearly ordered set such that for every non-empty subset W as least element, and by linearity it will be the first, it will be the union. Okay, so now you see how naturally he has entered in this very, very abstract notion. Okay, starting from analysis and this, and then obviously each mathematician wants to generalize and generalize his result. So he was generating sets of uniqueness, but how does he describe all these set of uniqueness that is coming to his mind? And that led to this concept of well-ordered set. Okay. Now each natural number is a well-ordered set. Set of natural numbers is a well-ordered set. And all the sets that I have described, you see set of natural numbers is linear as an ordered set, is isomorphic to 1 minus 1, 1 minus half, 1 minus 1/3, ... Okay? So take that and follow it up by 1. Again, this is a linearly ordered set because it is a set of real numbers. But in this set, every non-empty set has a first element. Okay? Then follow it up by another element. 1, 1 minus half, 1 minus 1/3, sorry, 0, 1 minus half, 1 minus 1/3, ... 1 and 2. That is the counterpart of infinity plus 1. Okay? Followed it up by 4. These are well-ordered sets. But if you want to do again, you have 2, 3, 4, ... I squeeze them in the interval 1 to 2. Okay?
Mohan,
Can
I just interrupt? We need to wind up a little soon.
Okay, yeah. I'm coming up now.
Right.
It's not too much. As I told you, I will not do. So all these sets he defines, and then it is not very hard to prove this theorem. Once you know the notion of well-ordered set, then you want to prove that for each u in, by the way, what is the time? I can't see.
It's about 5:36 p.m. 5:36. We are past 6 minutes. Okay.
Okay.
Very fascinating, but.
So now this transfinite induction, okay, and definition by transfinite induction is not very hard to generalize. And another thing that he noticed, you see, if you take a subset of real number, then the set of isolated points is a countable set. So he said that the set of uniqueness that he is defining is in some sense small. It is though infinite, but it is small. And then he showed that they can be enumerated, and he defined a countable set. Then he had a problem that is there a set of reals which is not countable? And he proved that set of real numbers itself is uncountable. And then he realized, oh, infinite sets are of different sizes. And then he put the ordering mod x less than mod x equal to mod y if there is a biject set. That is what he meant by psi. And showed that mod x is less than power set of mod x. And that led to the notion of cardinal numbers. And since I have already consumed a lot of time, I stop here. But let me go to this. So this is what I am saying, that by thinking that his set of uniqueness are though infinite, but somehow he got a feeling that it is a small set. And to make it precise, he introduced the notion of countable sets. And then he asked the question, is there a set which is subset of real which is not countable? Whether they cannot be enumerated elements. And he showed that the set of real numbers itself is such. And for the first time, there are two infinite sets of difference, so to speak, ij. And then that led him to describe cardinal number. Okay. So, but he was doing very general mathematics, so it led to a lot of paradoxes that you all know of by now, and which had a lot of impact. So this is the last slide. However, as we all know, that during his lifetime, there was a lot of controversy around, set theory. What kind of this is. And I will not mention the leaders of the two groups. One group called Cantor, Scientific Charlatan, Computer of Youth. And his work was declared a grave defeat in shifting mathematics. There was one group on this side, and I am sure many people here know who were they. Great topologists, great algebraists, and such. And there was another group which described his work as a paradise. That no, it's a great work. And according to Cantor himself, the fear of infinity is a form of myopia that destroys the possibility of being actual infinite, even though in its highest form has created and sustains. Okay? And this is where I stop. So I'm sorry I short off the time. So can I stop sharing? Or is there question and
Yeah.
huh?
You need. I mean, we have time for some quick questions. So if anybody has anything to ask, maybe
Well,
for 3 or
I
4
would be
minutes.
more interested in quick comments.
Or both comments and questions, and then of course they can directly interact with you subsequently.
Actually, you can
Yes,
surely
sir.
mention.
I can recognize you. Yeah.
You can surely mention the leader of the second group. There shouldn't be any problem. I mean,
No. I will not mention any name.
Leader of the who called Cantor's set theory of paradise. I think surely you can mention that. That will be nice to know.
Well, I think many people know. But okay, for
Students,
a student,
will not know.
for
Students
a
will not know. I
student,
think students should know that.
a student it is Hilbert.
Yeah.
Okay. And for others, I think Amatto will prefer that I don't say the name. Huh?
No, I don't mind. I mean,
Okay. Huh? By the way, Amatto, I started with Brahmagupta, like you started. Huh? Okay, so this is not a comment, but what I want to say, if you have taken this lesson, that you see that it was a natural development in mathematics. And that is the point I want to make. I have not taught you. I know that I am spending much more time on analysis. But how this concept, so this is true, my title is quite appropriate, The Birth of Set Theory. Later on the stories now people know, the developments people know. But how it was born is not known. And it also gives the idea that no, set theory has impact on math. It is useful. Okay, so PSS, let me stop sharing. And when you ask me, I will quit.